Okay, so I'm going to go through this protection and control. Some of the stuff is pretty straightforward, laid out again extremely well as far as it goes in the module and referencing rules into the code book. Some of the calculation, well, not really calculations, but scenarios, I guess, for tap conductors is probably one of the more confusing parts. So, again, they do a really solid job here, though, going through them. So, I'll try and go through the objective exercises just to show you how I got the answers. They were even a little bit better with their feedback in the objective exercises in this module. So, they did do a rewrite, so maybe that's part of their game, is to improve their feedback on the actual exercise questions. So I'm just going to kind of go through this objective by objective, but again, probably won't hit everything just because some of it is just kind of read and retain stuff. But yeah, well, I'll hit through the points that we really want to make sure and stuff that I see commonly having struggles with or make mistakes with. So again, this is about protection and control. So basically determining the overcurrent, okay, whether it could be a fuse or a breaker, or again, whether we need a GFI or GFCI based on our circuit, and it's going to tell us how we need to do that. So they go through first and do the definition of a short circuit. Okay, there's a difference obviously between a short circuit and an overload condition, and some forms of protection will do both, like a circuit breaker. Short circuit, again, line to line, phase to ground, phase to neutral. Okay, that's going to cause a short and going to be an extremely high value of current. It's going to create a strong magnetic field and a lot of heat, so we need to shut that down ASAP. Okay, but it's a lot of current we're going to see through there. Then the difference between a short circuit and an overload is just potentially that a circuit is being loaded a little bit more than it needs to be, okay, or even, I don't know if they say an actual percentage, but we're basically drawing too much on the circuit for what it's capable, and it won't trip instantly, but could trip over time. So that excess of current draw, because it's either being asked to pull too much through the design circuit, or I guess you're just potentially just maybe it's undersized for the actual piece of equipment. You'll see a trip due to overload, which basically I'm drawing current for too long, heats up the cable, and then we'll usually, in the case of a breaker, will move a bimetal strip and then trip due to overload as well. Okay, so those are the two things we have to worry about: short circuit and overload, and the terms. Location, again, they go through and they'll tell you where to read the rule. This stuff's pretty straightforward, not too terrible. Again, they're saying in 14100, so it says that right in the beginning of the rule here, it kind of tells you that we're going to need where we need a breaker and where it can be omitted. So this is saying each ungrounded conductor shall be protected by an overcurrent device at the point where it receives the supply and each point where the size of the conductor is decreased. Okay, so then they say, except, okay, that the protection shall be permitted to be omitted in each of the following cases. So it goes through and tells you where, you know what, you can reduce the size and we don't need a breaker. So that's what this 14100 is going to get us into. So they're talk about it here. First one they go through in this example is basically just a reduction potentially due to an increase due to a volt drop scenario. So I have a 15 amp overcurrent, have number 10s, and then I've gone down to 14s. The reason why it's okay is just because the breaker is going to protect, is rated to protect either one of these. And again, this is due to volt drop. Okay, so there's an increase of that wire due to volt drop. And this will properly protect the smaller of the two conductors. So this scenario is good. Okay, so that's first one. Then it gets into these different scenarios of the length of a tap conductor. Okay, so they got a few questions, and we definitely have questions in our blackboard about this as well too. We got an 80 amp load fed from a 90 amp circuit breaker, which is supplied by a splitter. The splitter is fed by a 500 kcmil conductor protected by a 400 amp circuit breaker. All the equipment temperature terminations are 75 degrees. So the size of the tap at point A, so here's our tap conductor here. That's the point where we have a large, so we got 500 kc mil wires in this splitter, and we're going to split down to a smaller conductor for this load. Okay, and we don't need to have a breaker in here as long as we follow certain rules. So it depends on a few factors. 14100B says if the tap conductor is 3 meters or less, the conductor must be rated to carry the load current. Okay, so this current here, and also rated at not less than the switchboard, panel board, or control device. Okay, so that could be depending if I got a panel, if I got a disconnect here, it's the rating of the actual switchboard, panel board, or control device. It must also be run in non-ventilated raceways or be either an armored cable or metal sheath cable. In this case, tap conductor A is required to be rated for at least 90 amps, okay, because that's the rating of the switchboard, panel board, or control device. So because it's 3 meters or less, that's what we're using. Again, according to table 2, we go to look for 90, and we can see that we can use a number 3. So that's how we size it in this scenario. 14C is saying where the smaller conductor is less than 7.5, is suitably protected, okay, and then have an ampacity of at least 1/3 that of the feeder conductors. So these are the feeder conductors, the 500 kc mil, and have an ampacity equal or greater to that of the overcurrent device that it feeds, okay, which in this case again would be that 90. So it's saying for tap conductor A, it needs to be either the greater of the 90, okay, that 90 there from that breaker that the circuit breaker is rated at, or 1/3 the ampacity of the 500 kc mil conductor. So we have to go to table 2 and see that a 500 kc mil is rated at 380 amps. So 1/3 of that, so we just divide by 3, is 126.7. Accordingly, if tap conductor A fell within the requirements of this rule, would carry an ampacity of 126.7. This would be a number 1 from table 2 at the 75 degree. Okay, so basically what they're saying is you choose the larger of those two. When you get into the between 3 and or over 3 and under 7.5, we're going to look at the overcurrent, and we're going to look at 1/3 of this. So that's at 126.7 amps, and we see which one's larger. Again, if we're in between 3 and 7.5. So this is the larger, so that's what we would use to size the tap conductor. If we didn't have this at 7.5 and we had it larger than that, basically we have to feed this now with 500 kc mil wires. Okay, so it's the length of this tap that allows us to avoid having to pull a full size conductor of the same size that's feeding this splitter. So the reduction of that is allowed because of the length of this tap. Okay, and again, whether we're at 3 meters or less, or between that and 7.5. Okay, so D allows tap conductor size smaller than the overcurrent device. It's protected by, if it's for feeding a power distribution transformer rated over 750, so long as the primary has protection as Rule 2650. Tap conductors must also terminate in that overcurrent device, which cannot exceed the ampacity of the tap conductor. Okay, so that's feeding a transformer. That's what D is going to be talking about. So they show it here. Again, we have our feeder conductor, our tap. This is what the primary overcurrent they were talking about here. And then the secondary overcurrent device. So ampacity not less than the secondary overcurrent device rating. Okay, so 4100E is for tap conductor that feeds control equipment. It allows the tap conductor to be sized smaller than the overcurrent device, protecting it, but must be. And so again, this is for control conductors. So they're just going through each rule, or each sub-rule of 14100 with examples. So again, must be at least 1/3 of the ampacity of the overcurrent device protecting it, minimum of number 14, and located external to the control equipment closure. So here's a scenario for the control wires. So we have our branch overcurrent device, and then we have feeders going to feed the actual load, and then we want to tap off that to go to a control device, okay, or to a, in this case, a stop start. So the first thing you do to size this wire is, because it has to be at least 1/3 the ampacity of the overcurrent device, is you just take the overcurrent rating, divide by 3, and that'll tell you the minimum ampacity of the conductor that you need. Again, it has to be at least a number 14, but could end up being larger depending on the size of the overcurrent. So if you take 60 divided by 3, you get 20 amp, and then that's how you can size your tap off here for your control. Okay, F is going into the transformer. Let's just see. Allows tap conductor rated less than 1/3 if the following conditions. So the tap conductor must have ampacity at least 1/3 of the feeder. Secondary must have an ampacity not less than that of the primary tap. Secondary conductor. So the total length. Okay. So go through the objective exercise. I'll go through that and we'll show you how some of these are done. I have another. I have a PowerPoint of some of those tap conductors too that I'll also add to the class so that you can see some examples of all these. Okay, so that you kind of just put a general example for all that. I'll put some ones and it'll tell you every rule we go to in order to solve the question. So yeah, just to kind of touch on these objective 1 exercise. So let's just look at number 2. Got a 2.6 long tap and a 60 amp overcurrent device. So I usually draw these out, helps me out. So we know we're in that under 3 meters or 3 meters and under. And it says we got tap conductors running EMT from a 300 amp splitter fed with 350 kc mil conductors. If all terminations and equipment are rated 75 degrees, what's the minimum size of the tap? So what we got to look at, again, we would have a load down here as well too. But they haven't really told us about that. We don't need to know, in all fairness. What we're doing is saying that if this is 3 meters or under, just like it said in that example, we use the rating of the control device or switchboard, panel board. So that's what we're going to use in this case because of this length. So we can just use the 60 amp here from the overcurrent device and then go size a wire based on that. So we use a number 6, it's good for 65 amps based on that 60 amp overcurrent. The next example gets us into the other section of a tap length, which is that above 3 and above 3 and between 7.5. So we have 4.8 meters. In this case, again, I tried to draw it out best I can to help myself out with the scenario. We got a 500 amp splitter fed with parallel 250s. So we got 250 kc mils, parallel runs. Again, the rule says that we're taking 1/3 of the conductor ampacity. So don't get confused about a splitter rating. That has nothing to do with it. Just because it's rated at 500, that's not what we're dividing by 3. Okay, we have to find the conductor ampacity first. So the fact that these are in this 4.8 section, we got to look at either the overcurrent device or the ampacity of the 1/3 of the feeder conductor and choose the larger. So we're looking at the 100 amp, and then we're going to compare when we get 1/3 of the conductor ampacity. So in this case, it's the 250s. They're good for 255 amps, but they're parallel runs. So I take that 255, which is what it's rated for, the 250s, times it by 2, I get 510 amps. Then I divide that ampacity by 3, I get 170 amps. That's the other number I'm comparing. So I'm comparing between the 100 and the 170. The 170 is larger, so I go to table 2 on a 75 degree, and I'm going to have to use 2 aughts there because they're rated for 175. But again, 2 aught here, still large, but definitely not as large as running, obviously, parallel 250s to that. So still an advantage. Okay, so you might have seen in your experience that you'll see a splitter and you'll see a bunch of disconnects right above it, like in a service room or control room or something. You'll see all these disconnects really close to the splitter where they're getting their supply from out of this splitter. The reason they're doing that is to take advantage of these rules. If I can get these tap conductors lower, they're potentially going to be a smaller size. So if you didn't have this close enough, again, if you had this over 7.5 meters, you'd be pulling parallel 250s to this 100 amp circuit breaker, which again you want to avoid like the plague. So take advantage of that. That's why you potentially have seen that in the field as well too. Ground fault, again, it's pretty straightforward. Read through this, read the rules when they reference it. Tells you when you need it based on what type of circuit you have. Okay, the ratings, again, a lot of stuff's in the appendix B as well too, so make sure you're going through that. Selecting your overcurrent device, your rating. This is an important rule here. We've talked about it in previous rules, but 14104. Again, section 14 is one of the general sections of the code, so this is a general rule. They even make a point to say here, for circuits with motors, welders, transformers, these ratings may be exceeded because they have their own rules for sizing overcurrent device. So the rules for motors, welders, transformers, they're not part of the general, so they would trump this rule, okay? But in general, we have to adhere to this rule here, where it's basically saying I can only put a 15 amp on a number, again, we'll talk about copper, a 14 gauge wire can only go on a 15, a 12 can go on a 20, and a 10 can go on a 30. Again, that's copper. There is aluminum as well too. Okay, but those are maximum. So even if we get to a calculated value, and because these wires they're rated for higher current than that, but this rule says we cannot put them on a larger break than that. And we'll just show you on table 2 where it's referring to that. So on table 2, you can see that these 14, 12, and 10 all have this little kind of double S subscript notation. If you go to the notes, it'll tell you right there to see rule 14104.2. Okay, and that's going to tell you that even though these ampacities for these wires are larger, depending on what temperature you're going to use, right? So that's kind of the caveat. They're saying, hey, even if you're going out 75 or the 90, I can see these are rated for higher values of current, but in general, we're still going to limit the overcurrent that you can put on those wires. Okay, so that's an important rule there. So it does go through an example here too of the difference between the minimum rating and the maximum rating of an overcurrent as well. So that's important because you really got to watch the question. You could get it wrong just because you're doing everything right, but you gave them the max when they were asking for a minimum. So basically the minimum just it has to cover the load. Okay, so in this example, they're talking about a minimum rating of an overcurrent device used for 30 amp, non-continuous. All equipment temperatures are rated at, or terminations are rated at 75 degrees. So the minimum rating is we're just basically covered on the load. Okay, so in this case, it's 38 amps. So we'll go to table 13, and I'd use a 40 amp overcurrent device. That would be my minimum overcurrent. But then they say, well, what if there's a maximum? So then I would size the wire to the load first. So at 38 amp load, I'm going to go to table 2 under the 75 degree, and I'm going to have to go up to a number 8 that's good for 50 amps. Okay, so that's what they're saying here. Number 8 is rated at 50 amps. Then I would go to table 13 and pick a 50 amp. So the maximum would be a 50 amp, the minimum would be 40. Okay, so just watch the terms on that. Usually what we say is the conductor size for the load, the overcurrent size for the conductor. That's because normally we're talking about the maximum. Okay, but watch, if they do say the minimum, don't get caught on that. Continuous loads. The rating of the overcurrent device, basically your rating can be either 100 or 80%. Appendix B states that basically if it doesn't say it, the default is 80. Okay, so a lot of these questions are going to list them for us, which is awesome, but if they don't, the default is 80. So if you've been dividing your continuous loads by 0.8 the whole time, if it's not stated, you're using the default already, and potentially unbeknownst to yourself. So continuous loads. Again, it's how long are they on for? They're going to be on for more than a 1 hour and a 2 hour period, again at a certain rating here, 225 amps, or 3 hours and a 6 hour. What does that tell me is that it's basically on longer than it's off. Okay, and if it's on for a long time, it's going to be drawing current for a long time, and then the conductor is going to get hot because of that. Okay, so what we do is we upsize, again, inflate the ampacity before we choose a conductor. Kind of like a distance correction factor. or another type of correction factor based on heat or anything like that. Where again, it's not that the load's going to draw more, it's just we're going to do that before we pick the conductor. So in this example, it's got a 52 amp load. Again, it's continuous, okay, so that's important. And the overcurrent device is rated 80%, so it told us right there what it's rated at. First, the calculated load needs to be determined from the load current. Okay, so what they're doing is taking the load current divided by 0.8, and we get this new ampacity. Again, it's not that the load is going to draw this, it's going to draw 52 amps, but it's going to do it for a lot, okay, or a long period of time. So if we inflate that ampacity prior to going to the table 2, then we use that new inflated ampacity to size our conductor. Then we know that even though that load is going to be on for quite some time, it's not going to get as hot because we've basically upsized the conductor to make sure that we've accounted for that. Okay, so then it says you can use for 65 amps, you're going to use a number 6. Again, go on table 13, and we go to table 13, and we says that, and it says there anything between 61 and 70 amps, we're going to put a 70 amp overcurrent on. Okay, so table 13 is our go-to again for sizing our overcurrent device. That's regardless of breakers or fuses. Interrupting rating of fuses. So let's start talking about fuses now. Again, have 2 ratings. Have your continuous current rating, which is what it's able to see all the time, and then an interrupting rating, okay, what it can safely interrupt. So an extremely high value of current that it's got to be able to safely interrupt if it sees. So basically open if it sees that. If it can't, we could potentially have all kinds of problems. Okay, it gives you the maximum, the minimum required interrupting ratings for overcurrent devices, again based on the amperage and voltage. 10,000 amps for fuses, 10,000 for breakers above 100 amp and 250 volt, and then 5,000 for 100 amp or less and 250 or less. Okay, again, this stuff's not too terrible. We do talk about short circuit ratings too. To find the available short circuit current, we use the percent impedance, just like we did in 3rd year for transformers. So basically what we got to do is find the current of the secondary, and then we can use the percent impedance to find the maximum current. So in this question here, the thing we really want to just watch out for is it single phase or 3-phase, because that changes obviously our total formula. So in this case, we got a 100 kVA, 600 to 122.40. So we're going to use this secondary voltage, but we're going to use the maximum secondary voltage, that 240. Again, we don't have to use √3 because this is a single phase transformer. So basically what we're doing is using the S total formula. We're going VA divided by volts, which would give us our current. Then we're timesing that by the percent. Okay, so you'd have to put that in at 0.045, and then you'll get your, or maybe not because they're times by 100. Sorry, I do this different. I do it where I take 100 VA, I divide by 240, then I get my I of my secondary, then I take that divided by my 0.045, and I get the same answer. Okay, that's just how I do it in 3rd year, so that's how I still do it. It's going to give you, that's the minimum, the maximum short circuit current of that. So that's what we would basically have to size our overcurrent device on. Okay, it had to be greater than that because that's the, to me, I look at that as a minimum value. Because then, if that's what it's going to see, we need something that's rated higher than that so that it can safely interrupt that value. Okay, example 2, basically the same kind of deal. It's just got that √3 in there, okay, because this is a 3-phase transformer. Okay, so make sure you go through and get those calculations. Make sure you get those values. Again, it has to be larger than that to safely interrupt that. Okay, so that's a maximum current you're going to get. So we need to, that's the minimum we're going to look at when we size our fuse or our overcurrent for that. Time current curves just kind of tells you that, short circuits we want to trip faster. Some overloads we do want to allow for a small amount of overload without tripping, okay, depending on the type of load. Motors for sure, because they have high inrush current, we want to be able to see a little bit of a overload prior, and then it drops down to full load current. So there are scenarios where we can add, or we can have a little bit overload and it's okay. Again, coordinated overcurrents, not too terrible, read through that. Control device, disconnecting means, These are standard switch ratings. This is what, when we size those taps, when it says the rating of the panel board, switchboard, okay, that's these ratings normally is what you're going to see on those. Isolating switches, general use, just be careful. There's a note here about trade stuff that we normally talk about, and the code's different between a disconnect switch. We often will call a general use switch a disconnect, okay, but they don't do it in here, so make sure you read up on that. Solid state devices. So yeah, that's kind of it here. The self-test. So this is new in this module. They never had this self-test before. So just to kind of, I guess I went through these. I do it again on a separate piece. So just go through these, and then these top ones, because they're probably the harder ones of these. So again, we got a fusible safety switch, connect to a 600 amp splitter. So that's this question here, sorry, number 1 down here. They are not greater than 3 meters in length. 150 amp continuous load fed from the safety switch, 75 degrees, and rated at 80%. So this is the question here. So we got a 600 amp splitter. We started with the load. I always draw this out. I start at the load and work my way up this way. So I took my 150 divided by 0.8 because it's continuous, got my inflated ampacity, then sized this conductor off of that. So I used a 3/0 off the 75 degree table, which is good for 200 amps. So then I would have a 200 amp overcurrent. So now, because this guy is, I think it said, didn't really say, it just said they're not greater than 3. Okay, so 3 or less. Then we get into a scenario where we're using this to size our conductor. So we'll use 3/0 there for that tap conductor. Okay, fusible safety switch is connected, so there's number 2 here. An 800 amp splitter, it's fed with parallel 600 kc mils, 250 amp continuous load is connected to the safety switch, all termination of 75 degree and 80% operation. So now we're looking at number 2 here. So again, I start at the bottom, I get my load, I increase it because it's continuous, so now I'm using the 312.5 amps to size the conductor from my, I think it's, did it say a fuse? Yes, a fuse here. Okay, and then we size that, so we got to run 400 kc mils from the load, not necessarily a motor. Okay, I just happen to draw it like that all the time. Not a motor, because we would size it totally different because of that, so we'll just call this a load. Okay. This conductor here, again, sized off this 312, so we're going to pull 400s there because they're good for 335 amp. That's what's going to dictate the size of this fuse. So when we go to table 13, the 335 is going to put us into 350, okay, from table 13. Now, this is a scenario now, again, where we're either using this, or we're going to use a third of the feeders, whichever's largest. So because I have parallel runs, I find out what the 600s are good for. They're good for 420 amps from table 2, 75 degrees. Times that by 2, get 840. Now I'm going to use the third of my feeder conductor rule, so I get 280 amps. Now I'm looking at which is going to be larger of the two that I'm looking at. So this one's going to be larger here. So if I go to table 2, I'm looking for 350 amps, and I got to go up to 500 kc mil. Okay, so I got to use 500s here because we're using this as the rating, not the load ampacity, not this wire. We're sizing this from the wire, then we're sizing this from here. Again, also checking this and picking the larger of the two. The tap conductors for the control, again, I just did kind of what the module said. You basically just take the 100 amp circuit breaker and you divide it by 3. That'll give you your minimum ampacity, and then you go to table 2 and find your conductor based off that. So I just took my 100 amp circuit breaker, divided by 3, got 33.3 amps. So then I sized this. Again, this is a minimum 14, but in this case we can go up to a number 10 based on the, because we have to follow that rule about it can't be larger than 300%. Okay, so that's probably the hardest ones you're going to get, but go through those objective exercises. I'm going to post the this PowerPoint I have too, again, just for some extra stuff. I'll show you here. It's just goes through and it will, I'll probably just do a PDF of it, and it's going to tell you some different, so there's a splitter where we're topping off and reducing the size. Sorry. This will be some different examples about continuous loads, sizing these conductors based off the rule. Okay, I usually, again, I'd go through this in class, but I'll post it up there, and then if it helps, great. If you have questions about it, just let me know.